Here's sample test 1, problem number 6. Your rocket is launched with an acceleration of 8 meters per second squared and travels 600 meters upward before its engine turns off. How high does the rocket go? How long is the rocket in the air? This is really two problems in one. It's a bonus problem because we're going to have to deal with constant acceleration over two legs, and we can only use our kinematic equations over intervals of constant acceleration. So we have to treat it as two different problems. So we start off with the rocket ship taking off. It has an initial velocity of 0 starting from rest. We're told its acceleration is 8 meters per second squared, so that's what it is no matter what. It's working against gravity, but it is achieving an acceleration of 8 meters per second squared. Everything in the up direction. Final velocity we don't know. Let's call it V1. It's going to go some kind of displacement, which we don't know. And it's going to do it in some kind of time that we don't know. So there's a number of things that we don't know. Actually, we do know it's displacement. That's 600 meters before the engine turns off. So we have three things we do know in this first leg. And then in the second leg, we're going to go against gravity. The engine shuts off. We're going to start off with some initial velocity, which we don't know, but it will be equal to the final velocity that we had from the first leg in this second leg of the journey. And we're going to have the acceleration of gravity working against us, negative 9.8 meters per second squared, because we're going with a positive velocity in an upward direction and gravity's in the opposite direction. We're going to have some kind of displacement, which we need to find, some time that we need to find, and our final velocity is actually going to be 0 because we're going to go to some maximum height and we're going to stop there. So our final velocity at that maximum height will be 0. So that is our second leg. So we have a displacement delta y1 and another displacement delta y2 for these two different legs. Now if we look at the first leg, we know three kinematic variables, and we can find the fourth one. For instance, we can find the final velocity of the leg in leg number 1, which would be our initial velocity for leg number 2. So using that, we have final velocity squared equals initial velocity squared plus 2 times acceleration delta y1. This is kinematic equation number 3. And in this case, we started from 0. So our initial velocity is 0. And solving for final velocity, we have our final velocity will be equal to 2 times acceleration delta y1 square root. And that is going to be equal to 2 times 8 times 600 square root. And that's equal to 97.98, so we'll just say 98.0 meters per second is our final velocity, which indeed would be our initial velocity for the second leg, 98 meters per second. Hence, we can find out what our second displacement is because we know our initial velocity, we know our acceleration, and we know our final velocity, and we want to find our displacement. So we can use kinematic equation number 3 again. We have that our final velocity squared equals our initial velocity squared plus 2 times acceleration delta y2, and we want to find out delta y2 knowing that our final velocity for the second leg will be 0 because we're going to come to rest when we reach the maximum height. So delta y2 is going to equal a negative initial velocity squared divided by 2 times acceleration, which is going to be a negative 98 squared divided by 2 times a negative 9.8. And that is equal to 490 meters. Nice. So our final height, our total displacement, is the sum of these two displacements, delta y1 plus delta y2. And that is going to be equal to 600 meters plus 490 meters, which will be 1,090 meters. That's how high the rocket will go. How long is it in the air? Well, let's look at the first leg again. We know that our final velocity will equal our initial velocity plus acceleration times time 1. Our initial velocity for the first leg is 0. So T1 is going to equal our final velocity divided by acceleration, which is 98 meters per second divided by 8 meters per second squared, and that is equal to 12.25 seconds. And then for the second leg, we know we can do the same thing. Final velocity equals initial velocity plus acceleration times time 2. Our final velocity in this case is going to be 0, and our T2 is going to equal a negative initial velocity divided by acceleration, which is a negative 98 divided by negative 9.8, which is 10 seconds. And this is truly a bonus problem because we need to find the time back down to the ground. And we know that that total displacement for leg 3 is going to be 1,090 meters as we go back down to the ground. So that's going to be our delta y3. Our acceleration is going to be a positive 9.8 meters per second squared as we're going downward in a positive direction. And our initial velocity is 0, and we want to find our time, T3. So we have delta y3 is equal to initial velocity times time plus 1/2 acceleration times time 3 squared. Initial velocity being 0, so our time T3 is going to equal 2 times delta y3 divided by acceleration square root. That's going to be 2 times 1,090 divided by 9.8 square root, and that is equal to 14.91 seconds. So our total time, which is T1 plus T2 plus T3, is 12.5 plus 10 plus 14.9, which is 22.5 plus 14.9, so 22.3 plus 14 plus 10 plus 14.9 is 37.2 seconds. So that is our total time in the air, 37.2 seconds.